Good afternoon friends, welcome once again. In previous lecture, there was one small mistake. While explaining the cross section of a beam, I had said that part of the section which is below the neutral axis is in compression, actually it is in tension side. So you just consider this as exactly opposite. Sorry for the mistake. We will continue with from the previous session now. Here, based on previous lecture, I have summarized some of the points, and we have to do some assumptions also before going to the further theory part. So, as per the previous session, we have very first definition, which is of plastic hinge. What is plastic hinge? We had seen in stages the stress distribution diagram of beam, rectangular cross section. So in that last part was, or the last stress distribution diagram was something like this, where complete cross section of the beam will develop yield stress value. So when this part or this stage appears, there is plastic hinge. So in words, we can define plastic hinge as a section at which all fibers have yielded, and hence for further any load, rotation takes place at the section without resisting any additional movement. It means the capacity of the section beyond this is zero. Okay. After this stage has arrived for any cross section, there is no additional movement it can resist. Next is plastic moment capacity. So plastic moment capacity is defined as the moment at which or it is the moment which makes all the fibers at the section to yield and thereby form a plastic hinge. Okay, so based on the previous session, these are two outcomes. Now assumptions. For going ahead, in case of any theory, we need assumptions. Like in stresses in beams or in strength of materials, we have seen number of assumptions. Many of the assumptions here are also common. One of the common assumption is second assumption. Plane section before bending remains plane after bending. That is, the outcome or the meaning of this assumption is shear deformation is negligible. Then what else is there? There is one additional new assumption. Stress strain relationship is idealized to straight lines, to two straight lines. Which are those two straight lines? In first session we have seen a normal stress strain behavior of the mild steel. Now that mild steel behavior is idealized as two straight lines. So up to yielding point, that is point C, this is one straight line, and whatever is the behavior of the material beyond point C, that is beyond lower yield point, it is assumed as horizontal straight line. So these are two straight lines. So instead of behavior something like this, we have idealized this stress strain behavior as two straight lines. This is what our first assumption is. Second is common. Third, relationship between compressive stresses and compressive strains is same as between tensile stress and tensile strain. What is the meaning? If you see here, at a depth small d below the neutral axis, whatever is the stress and strain developed at this level, same relationship will be there at a depth d above the neutral axis. It means area of the section below the neutral axis and above the neutral axis will be same, but it is applicable only for symmetric cross sections. Next, in case of fully plastic movement, plastic hinge forms like this and it undergoes rotation, yes, but bending moment remains constant. Bending moment remains constant. Then effect of axial load and stress is neglected. So this is common assumption from SOM theory, and deflections are small. This is again a common assumption. So these are assumptions and these two definitions. Now in the next part we shall see the shape factor concept. Thank you. Good afternoon friends and welcome. Now we shall see the concept of shape factor, which is very important in plastic analysis. Okay. Shape factor is nothing but one ratio of two moments. So we will go to last semester's theory of bending stresses. We have this famous equation F by Y, F or sigma, okay, is equal to M upon I is equal to E upon R. So from this we can get M is equal to F into I upon Y. M is equal to F into I upon Y. So I upon Y is nothing but Z. I upon Y is nothing but Z, which is section modulus. Now this is, since this is from strength of materials theory, this is elastic. So whatever the moment we are getting is elastic, and this section modulus is also elastic. Okay. Now similar to this we can write plastic moment capacity as F into Z. So shape factor S is defined as MP upon ME, which is to be found as ZP upon ZE, because if we substitute MP as F times ZP and ME is equal to F times ZE, F gets cancelled. So this is nothing but a ratio of plastic section modulus to elastic section modulus. So now we will try to find out shape factor for different cross sections, which are standard results. Okay, so we'll start with the simplest of the shape factors, which is rectangular cross section. So here is one rectangular cross section whose width we shall assume as small b and overall depth we shall assume as capital D. Okay, so B by D is the cross section and we have to find out shape factor for rectangular cross section. So we have to find these two values. So one of them is ZE, which is simple, we can find out from the theory of strength of materials, elastic analysis. So ZE is equal to S I upon Y. Okay, ZE is equal to I upon Y. Now what is Y? Y is distance of extreme fiber stress from the neutral axis. Now where is the neutral axis for rectangular cross section? It is exactly at half the depth of the beam. So our Y value is D by 2. Okay, what will be I? Moment of inertia of a rectangular cross section, BD cube by 12. So we shall substitute both these values in this ratio. Okay, so I is equal to B into capital D cube upon 12, this is I value, divided by y is distance of extreme fiber stress from neutral axis, so which is d by 2. So what will be this ratio? ZE is equal to b into this 1 power of d gets reduced, so d square, okay, into this 2 becomes in the numerator, 12 is as it is in the denominator, so this is vd square upon 6. This is simple. ZE. Now ZP is plastic section modulus. Okay, plastic section modulus means, now what is Z? Z is I upon Y, or stress into area. Stress into area. So as per the assumptions in plastic analysis, since the section is, cross section is symmetric, we have equal area below the plastic neutral axis as well as above the plastic neutral axis. Neutral axis coincides with plastic neutral axis because cross section is symmetric. So area above the neutral axis, plastic neutral axis, is equal to area below the plastic neutral axis. So we shall call these areas as compression area and tension area. So area in compression into IC plus area in tension into YT. Okay, both are equal, so we can write this as 2 times AC into IC because both areas are equal. So this is equal to 2 times. Now how much is the area in compression zone? You take any area now. So area in compression zone is B into depth d by 2. So this is AC multiplied by YC. So 2 times AC into YC. So this is YC. YC value is nothing but distance of centroidal distance of compression zone from neutral axis. So where is the centroid of compression zone? Compression zone is now either we can consider any area above the neutral axis or below the neutral axis because both are equal areas. So these are the 2 points. To find out any of the distance of these points from neutral axis. So this is rectangle of d by 2. So centroid of rectangle is at half of the depth. Depth is d by 2 for area in compression. So this centroidal point is located at a distance of half of d by 2, which is nothing but d by 4. So YC is d by 4. Okay, not like this, d by 2. Okay, so here actually it is this distance. Okay, so any of the distance will be same. So YC is d by 4, hence we are getting ZP as BD square by 4. So substitute now ZP and ZE in this shape factor ratio. We will get this value as 6 by 4. So 6 by 4 is 1.5. Okay, so shape factor for a rectangular cross section is 1.5, which is constant. Thank you.